Hello, and welcome to more astronomy lectures. This time we're going to do a bit of a census of sorts of stars. This census will be mostly about how massive stars are, how large they are. So just like the US does a census every 10 years, go out and try to basically just see who's living in the United States. This celestial census is sort of like looking out what kind of stars exist in the universe. This is a nice picture of a field of stars. So we'll be looking at things like the size, the mass, the temperature, luminosity. Remember, luminosity was like the total energy output of a star. So most of the cluster in this image is in the small Magellanic Cloud, which is sort of this cluster of objects that are sort of orbiting our galaxy. The book makes a point of examining the fact that when you try to do a census, it can be difficult to not be biased in your census, to only sort of like look at a particular group and see what is going on with that group, like how massive the stars are that are just kind of near us, right? We're not going to worry too much about that. Like that gets into like statistics well outside of this course. We're just going to kind of assume that we've done a pretty good job in not having a biased census, right? We look at a whole bunch of different stars at different distances from us, different places in the galaxy, different galaxies in the universe, right? And people have put a lot of work into creating this sort of census of all these objects, mostly stars, that is fairly well representative of all the stars that are actually out there. So before talking about the temperatures, the masses, size of the stars, it's going to be really useful to remember and just kind of put out there the way that we talk about these things. And in science, when you say like the way I'm telling you about a particular quantity, like temperature, that means what are the units that we're talking about? The units that we've been using pretty much the whole time are Kelvin, capital K. Day-to-day life, you probably are more familiar with Fahrenheit. There's also Celsius. Just some sort of benchmarks there. The surface of the sun, you remember I told you, on average is about 5,800 Kelvin. Room temperature, or even like body temperature, they're all that different in terms of temperatures of stars, is about 300 Kelvin. And on the Kelvin scale, when you get to zero, that's zero motion overall. Hopefully you remember I told you about temperature being just a measure of the motion of all the atoms and molecules that make up whatever it is, like me, or like this air, jiggling around stuff. So the more jiggling around overall, the higher the temperature. So you slow that jiggling down more and more and more and more and more. Eventually you get to no jiggling, no motion at all. That's 0 Kelvin, absolute 0. When we talk about mass, we've used kilograms. I think mostly talking about stuff in the solar system like planets. And kilogram is something like 2 pounds-ish. But yeah, now that we're going to be talking about stars, these things are generally much bigger than planets, and like our sun, in terms of kilograms, is like 10 to the 30th kilograms. There's a whole lot of kilograms. It's not so useful to keep talking in those units. Instead, we're going to talk a lot in solar masses, right? So how many times the sun's mass are these other stars? So it could be like 2 solar masses is twice as massive as our sun. Or 1/3 of the solar mass, right? It's 1/3 the mass of our sun. In energy output, right, that's luminosity. More regularly, you're probably familiar with watts or have seen watts as a usage, particularly for like lamps, light bulbs. Again, not so useful now when we're talking about stars is because these huge amount of watts that are being put out by a given star. Like our sun, something like 10 to the 26 watts. You do the same kind of thing then, is talk about the luminosity of stars. We'll talk about it relative to our sun. Again, so something could be like twice as luminous as our star, or 10 times as luminous as our star. When we talk about size, before we might have used like kilometers, like for the diameter of planets. Now, again, we're going to be doing the same kind of thing. We're talking about solar diameter. So how many times larger is a star than our sun, or how many times smaller? And just to keep in mind, our sun is about 1,000,000 kilometers across. About 110 Earth diameters, I think is what it turns out. Finally, distance, right? So size and distance are both length measurements, but when we talk about size, it's helpful just to talk about it in terms of the diameter of our sun versus the size of other stars. We're talking about distance, though, between stars. That gets much larger than kilometers, much larger than solar diameters, and even larger than astronomical units. So for a while in the solar system, we used the AU, the astronomical unit, which is basically like the distance from the sun to the Earth. That works very well when talking about planetary systems or within a solar system. Once we get out of solar systems and look at distance between stars, we're going to start using what's known as a light year. And this is how far light travels in 1 year. Turns out to be about 10 trillion kilometers. Very, 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 very far, right? 63,000 astronomical units. If you remember, Jupiter's orbit is like 10 AU. I think Neptune's is like 30, maybe. So a light year is thousands of times larger than our solar system. There's also something called a parsec. I think I'm going to try to just stick with light year. Parsec is like 4 light years or something like that, so they're really not that different. We're going to try to stick with light years. So we actually talked a good bit about the temperature of stars last lecture, I think. So the first thing we're going to do now is think about the masses of stars and give you a little bit of idea of how we measure the masses of stars, and then tell you a bit, kind of broadly speaking, of the census, like what kinds of masses are there. So one place where it becomes a little bit easier to measure the mass of stars is in binary star systems. That is something like this, where there's 2 stars that have formed kind of right next to each other, or very near to each other, and they're orbiting around each other. Binary systems, it turns out, are rather common. Our solar system is like a unitary star system, right? Just one sun. And that makes up something like half of the planetary systems that we see, right? So far as we can tell. Binary systems make up almost the other half, right? And then there's a decent amount still of 3 star systems, and then less of like 4 and 5. And that is to say that there are a good amount of binary star systems, right? So when we look out, we see a decent amount of these things. This animation here is showing like one kind of binary star system where the stars are about equal in size, equal in mass, and they nicely sort of orbit around each other. There's a whole range of binary star systems, though, and ways that they orbit each other. There's a whole other one where they're similar masses, but they're sort of orbiting like this. I'm pretty sure I told you about this a while ago. But just to remember that this is like one kind of binary system. It's a pretty simple one. Another case is actually something more like here, where one of the stars is so much smaller than the other one that it almost orbits like a planet, right? The really big star doesn't move all that much, and the other one just kind of orbits around it. The images on the left are of the nearest star system to us, which happens to be a binary star system. Actually, I think it's actually a triple star system, really. So Alpha Centauri has 2 stars that are orbiting each other, kind of similar to this. I think those 2 stars are about the size of our sun, and I think in image B there, they're indicating those like 2 stars. But those are the 2 stars that are orbiting sort of close to each other. In fact, there's actually a 3rd star that's a dwarf. It's a much smaller star, and it's also orbiting in this system, or it's gravitationally bound to this system. In the last lecture, we looked at the things you could tell from a binary system like this, depending on how the system's oriented relative to us, right? Like it could be this face-on one, where we're almost looking like down on the plane of the orbit. It could be this like edge-on thing, where we're looking like along the plane of the orbit, or along the plane of the binary stars, and anywhere in between there, right? Those are just the extremes, face-on and edge-on. If it was edge-on, we imagined using that kind of system before to watch like a star coming towards us, going away from us, coming towards us, going away from us. That motion towards us or away from us affects the light coming from that star. Doppler shifts the light from that star. Why is that useful, or why does a binary system we watch orbiting around each other give us some nice information? Well, you think back to Kepler's law, one of Kepler's law, which is actually then modified by Newton, that said the area that an orbit sweeps out is related to the period of that orbit, how long it takes to go around. A little bit more complicated, it's actually a cube of the area, so the area multiplied by itself 3 times, that's equal to the period of that orbit squared, or multiplied by itself once. And also on this side is the sum of the masses of the 2 stars here. So mass 1 plus mass 2. You write it a little bit more compactly. A cubed is equal to m1 plus m2 times p2. I don't really expect you to use this or implement this, but just saying that the masses and the area of the orbit and the period of the orbit are all related to each other, and they're related in a known way. So all that said, if we can measure the period of the orbit, how long these stars are taking to go around each other, and we measure the area of the orbit, and how big that orbit is overall, then we can directly get the total mass of that binary star system. Right? It's just that area cubed divided by the period squared. So that's the total masses. It turns out that if you can measure the speed of these stars, how fast they're actually moving in their orbit, not just the period and the area, but if you can measure their individual speeds, then you can actually disentangle the information about the mass to say what the individual masses of each of these stars is. So this is one way of measuring the mass of stars. There's a pretty cool image on the left. It's actually a compilation of a number of different images that shows a star system. There are actually 2 dwarf stars, I guess. And it looks like they're orbiting around a larger star in the middle. Like if you look in the very middle of that image, there's this ellipse drawn, and that's the orbit that the 2 dwarfs together are moving along. And so there must be a larger star that's right in the middle. It's kind of frustrating. I couldn't find more information about that. Anyway, as those 2 stars, those 2 dwarf stars together move around this orbit, they're also orbiting each other. So in April, and then February, and then October, and the next February, March, right? And you can see the progression of these 2 stars orbiting around each other. And just from watching them orbit around each other, we can get information about their mass. This looks particularly like more of the edge-on situation, right? We're sort of looking down on the orbit so we can see the 2 stars orbiting each other. And just to note then how we might get the individual speeds of these stars, well, remembering that watching the star come towards you or away from you, Doppler shifts the light from that star. So when it's coming towards you, the light from that star is shifted blue a little bit, or towards the blue. When it's going away from you, it's shifted a little bit towards the red. And how much that shift is directly related to the speed of that object. So when a star system is sort of edge-on, then we see one of those stars coming directly at us, the other one going directly away from us, and we can get information about their individual speeds that way, which again just allows us to sort of detangle the information about the mass. Right? Then you get the individual masses. This is a little bit of a side note. I just wanted to remind you that when we talk about looking at stars, we're not just thinking about looking in the visible range, right? Like if I look with my eyes, but like my eyes are really, really powerful, I can see a lot further, I can see a lot more stars, but I would only still be looking at visible light, right? Astronomy uses like the full range, pretty much, of the electromagnetic spectrum. So visible light is one little chunk in there, but there's also ultraviolet and X-ray and gamma ray, and there's also infrared, radio. The images here on the left is a visible, an image taken in the visible part of the spectrum, and you see a lot of dust in this part of Orion. It's the Orion, part of the Orion Nebula, which is in the constellation of Orion. If you try to look in the visible range, you see mostly dust. There's some stars where you don't really see a whole lot of them, or you don't really see most of them. Compare that to the right side here, which is an image taken in the infrared part of the spectrum, or looking at infrared light. You don't see any of that dust. Okay? Remember, infrared is basically like heat, so that dust isn't really emitting heat What is emitting heat are all these tiny other little stars, and most of those are dwarf stars, I believe. So this whole field of stars there that you don't really see in the visible spectrum, but see a lot more in infrared. And it's not that infrared is better than visible, they're just different parts of the spectrum allow us to see different things. The dust itself is also quite interesting too. Yeah, so just a reminder about that. Back to mass, right? That was just sort of one example of a way that we measure the mass of stars. So here's our sort of census of the masses of stars, right? Look around, we do a count of all the masses of all the stars that we can see, get a relatively even sampling. Turns out that most stars are either around the mass of our sun or smaller, right? 1 solar mass or less. There are a few stars that are quite a lot larger than our sun, 100 times as massive as our sun, and there are even a smaller subset of those that is really just enormous, right? 250 times the mass of our sun. So that's about the upper limit also of the mass of stars that we see, a couple hundred times the mass of our sun. The lower limit turns out to be about a 1/12 the mass of our sun. Down here then is an image of some stars, and along the bottom is the spectral class that we talked about last time. It goes from O, B, A, so the hottest stars on the right here, down to the coolest stars on the left. You remember our sun is class G2, so down there in G. Also shown here are sort of the temperature cutoffs for each of them. And as we'll see, the mass goes generally with the size of the star. So G is about the size of our sun. Most stars are around that size or smaller. There are some that are a bit bigger, and then there are some that are just gigantic. Not a lot. So a very interesting relationship comes up when you compare the masses of stars to their luminosities, to how much energy they're putting out. So if you just plot the mass of the star versus its luminosity, and those are both in terms of the sun, so solar masses to luminosity of the sun, meaning that our sun would be a 0.1 solar mass up to 1 luminosity. So at the very bottom of that cluster in the middle, sort of. But you plot a bunch of different ones, right? Some that are much more massive, plot their luminosity. Some that are less massive, plot their luminosity. Surprise, surprise, you get a pretty nice relationship. And beyond that, we could say it's a proportional relationship at least, right? As the mass of the star increases, its luminosity tends to increase. Over more here, up more. We could say that in another way, say the more massive the star is, the brighter it shines. And to be a little bit more exact, it's not just proportional, like 1-to-1. It turns out that the luminosity goes up as the 4th power of the mass, meaning that a star that is twice as massive as our sun would put out about 2 to the 4th, or 2 times 2 times 2, 16 times more energy than our sun. And so a couple of things to note here. For one, right, this isn't necessarily a true statement about the brightness of a star that you see with your eye when looking out in the night sky. Remember, that's the apparent brightness, and it depends on how far away the star is actually from us. We're thinking about the luminosity, so the total energy that's being put out by that star. Only a tiny bit of the full luminosity, or the full energy output from any star out in the sky is reaching us. There are a couple of points that don't really seem to fall on that line very well, and those turn out to be something we call white dwarfs, which I'm just going to have to wait to talk about more later. And the last thing to note here is that this relationship is true for most stars, right? It turns out it's true for about 90% of stars that we see. So who knows, whether you'd expect that relationship, whether you wouldn't expect that relationship, that the mass goes along with the brightness, I don't know, but it turns out to be the case. Moving on then to the size of stars, right? How wide they are, what's the diameter of those stars, particularly compared to like the size of our sun. Again, just going to give you an idea of how we might measure the diameter of a star. One way to do that is to look at this thing called the light curve, which is just the brightness of a star over time. And if we have stars that are like binary stars, where one of the stars is very large and the other one's not all that large and it's just orbiting around. As it orbits around, the much smaller star is putting out generally much less energy, right? The luminosity goes down a lot, the mass. So that star, the small one, is pretty dim relative to the big one, which also means that as it passes in front of the big star, it's blocking some of the light that would be coming from that main star to get to us. So that little star you call like the companion star, and it goes in front, starts blocking some of the light from the big star, and then eventually passes the other side, and all the light from the main star gets to us again. But if you think about it, the change from being like the full brightness of the main star to all the way down when the little star, the companion one, is in front of it, there's a certain amount of time it takes to change. And that time is related to how wide the companion star is, its size, and how fast it's orbiting. So in the picture on the left there, you go from like time 1, where the companion star is like just on the edge of the main star, to time 2, where the companion star is now totally in front of the main star. During that time, the companion star is blocking more and more of the big star's light until it gets to all the way in front, and then you're down here bottomed out, right? So the amount of time that it takes to go from up here to down here can tell us about the diameter of that companion star. Again, we also need to have information about its speed, and at least if it's a system like this, then it's sort of like edge on, and the Doppler shift in the light from that companion star can tell us about its speed. Those two things together, we can measure the size of that companion star. And it's not on here, but I mean, if we know how fast that little one's orbiting around and we watch it go in front and then move again, we could probably also get the diameter of the big star too. So watching one star pass around another one. This is one way we can measure the size of stars. A couple other ways that we measure the size of stars. One has to do with that process of occultation I told you about a while back. Just when one object moves behind another one, or the first object moves in front of the other one, same difference. How does that tell us about the diameter of something? Well, the images here are of Saturn passing behind the moon. So you watch from like the right to the left there, Saturn is like fully visible, and over time, we watch Saturn get slowly covered up by the moon. If we know their relative speeds, then we can actually use that time and this speed to get the distance that Saturn moves, right? And that's basically the diameter of Saturn. I'm pretty sure in this image, Saturn is so much further away that its motion is probably very small compared to the moon. So you're actually watching the moon just kind of cover up Saturn. We know how fast the moon is orbiting around us, how long it takes then to cover up Saturn completely, tells us how wide Saturn is. Yeah. This is a very nice technique. Unfortunately, it's only good for stars that are very close by. Beyond that, any star that you look at is basically just a point of light, and there's no real time difference between what's outside of the moon and behind the moon. But we can measure some stars' diameters like that. Another way has to do with something called the Stefan-Boltzmann law, which I didn't really tell you about, and we don't need to worry too much about, but to tell you here that the luminosity and the temperature of a star are directly related to the size of that star, the surface area in particular. And the surface area is just a function or is related to the radius and the diameter of that star. So if we know the luminosity and can measure the temperature of a star, we can actually tell how large it is because of this Stefan-Boltzmann law. And it just has to do with how objects radiate energy. They give off energy. This is another way we measure the size of a star. So here we are again, sort of census of sizes. Maybe not such a big surprise, but very similar to the masses. It turns out that most stars are about the size of the sun or smaller. A lot of them are smaller, which is about 1 million kilometers across. Some are much larger, and there are a few that are just gigantic. So we call the big ones giants, and the really big ones supergiants, and I think there's actually a class called hypergiants, which are even bigger, and there's probably only like a handful of those that we've spotted. So we're going to have a little video here that shows the size comparison of stars. I think it starts out with Earth, and then that compared to our sun, and then compare that to some of the much larger stars. Right? But remembering again, like our sun is actually larger than most stars that we see. Most stars are smaller than the sun or about the size of the sun. This is just a video to illuminate those kind of rare ones that are much larger, how much larger they are. So there's our Earth to the sun. Remember, the sun's about 110 Earths across. We're a tiny little thing next to our sun, but our sun next to this blue giant is a tiny little thing. It's like the sun of the Earth. But that giant next to one of these like super giants is not so big anymore. And then that one next to even the very largest, the last star I think in here is about the largest star, or the size of the largest star that we've seen. The second to the largest one is we call one of the supergiants, and that's actually about the size of Betelgeuse, star Betelgeuse, which is in Orion. And it's just crazy how large these things are, right? Betelgeuse is about the size of Jupiter's orbit. So if Betelgeuse was in our solar system, it would take up the area about out to the orbit of Jupiter. Just one more time, right? It's very interesting and sort of mind-boggling to think about these really, really large ones. Most of the stars that we've seen are not that large, right? These are kind of the exceptions, very rare, really, really large stars. This table just summarizes some of the things that we talked about in measuring the properties of stars, right? Like their temperature, their chemical composition, or what elements and atoms make up that star, luminosity, motion, rotation, how massive, the size or the diameter of stars, and just sort of very briefly reminding you how we measure some of these things. In the last lecture, I think we talked a bit about measuring the temperature and chemical composition. We haven't really talked about how we actually measure the luminosity, because that depends on the distance that stars are away from us. I mean, it's not that much of a stretch to go from how bright the object looks to me. If I also know the distance it is away, then it's really straightforward to say how luminous that star actually is. Can be complications, but for the most part, apparent brightness and the distance together pretty much tell us the luminosity of a star. We haven't really talked about finding distance yet, so yeah, we're just kind of assuming that we know the luminosity of these stars. So it's a nice sort of summary from the last lecture or two. So we've measured these different things about stars, their mass, size, luminosity, and temperature, classified them by their temperature with that O, B, A, F, the spectral classification. Now we're finally to the point where you can think about like looking at the relationship between any of these properties and seeing, is there any sort of nice relationship there? Like earlier we saw that the luminosity of most stars is proportional or goes along with the mass of that star. What other kinds of relationships are there like that? And just sort of prep you for what we're going to find, the book talks about looking at the relationship between like the height and the weight of people. If you just go around and measure people's height and weight and start plotting them, you probably get something like this. At least if you plot height going upwards here, meaning the smallest height is down here, the highest, tallest people are up here, and you plot weight actually going to the left. And so the lightest weight is over here, the heaviest weight is over to the left. Right? So up here are tall, heavy people. Down here on the right are short, light people. If you just went around and measured these things for a bunch of different people, plotted them like this, you'd probably get this kind of picture. Right. For the most part, height and weight are proportional. Most of your weight is made up of like your organs, your bones, and that just goes along with your height. The taller you are, the larger all your internal stuff is. However, there are exceptions, right? Like in this diagram, there are some people that were measured that are very heavy, but still rather short, sort of overweight. You'd end up being down there in the bottom left of this graph. There could also be people that are very skinny and very tall, sort of underweight. Right? So that would end up being in the upper right part of this diagram here. But for the most part, people fall along this line. that is then to set us up for plotting the temperature of stars versus their luminosity. So luminosity going up on the left there, and temperature, just like weight in the last one, is plotted from lowest to highest. Right? So the lowest temperatures are over here on the right, highest temperatures on the left. Why exactly it's plotted in this way, I'm sure it's just historical. Probably make more sense to do it the other way, but whatever, this is what it is. And if you make this plot of temperature versus luminosity, it's what we call an HR diagram for Hertz, Sprung, and Russell. And this diagram particularly is a sort of representative sample of stars, right? So that's all to say that if we look at the features of this plot, any relationships we see are good for stars in general. And the main relationship we do see is the same sort of thing we do with height and weight. Right? The hotter a star is, the more luminous it is. Right? All the way over on the left there, most of the stars that are in that O class or B class are very luminous. So things like Rigel and Spica. And that relationship goes all the way over. We follow this sort of main line of dots there down to the bottom right. The coolest stars are the least luminous, the least bright, or the dimmest. So we go from that hot and bright in the upper left all the way down to the cool and the dim in the bottom right. A number of stars are given names on there. The Sun is pointed out. Right, again, it's like a G-class star. Alpha Centauri A is one of those in that star system I mentioned earlier. It's our sort of nearest neighbor star. Proxima Centauri, all the way at the bottom right there, is also in that system, but it's like a dwarf star. It's very cool and very dim. So that main sort of line of stars is what we call the main sequence. And most of the stars that we have observed fall on the main sequence. There are, of course, exceptions, just like there were in the height and weight diagram. Right? There are some stars in the upper right here. Those are stars that are very cool, relatively speaking at least, but very luminous. They give off a lot of light. In general, those stars in the upper right are the giants. Those are the very large stars. There's also this other cluster of stars in the bottom left, which, left being very hot, but in the bottom there, very low luminosity, right? So very hot, but still very dim. And those stars in general are white dwarfs. I mentioned white dwarfs a few times. I think I've said it before, but that is one possibility or one sort of late stage of a star's life. It turns out also that giants are late stages of stars' lives. For the most part, a star, most of its life, is somewhere on that main sequence. Like our sun right there, sort of the middle-ish of the main sequence, spectral class G, about 6,000 Kelvin, and luminosity 1. So I think I got maybe ahead of myself on the last slide a little bit, but this is just another HR diagram, more dot spot on there. Actually, to point out, in this HR diagram, there's also color in the background, and if you remember, the colors generally correspond to the spectral classes there. Like our sun is like yellowish. The really cooler ones, K and M, are generally red. Really, really hot ones like blue, purple. This one, no color, but just more stars plotted on there. And most of the stars that we see fall on this main sequence, or somewhere along there, right? Something like a spectral class B in luminosity that's like 100 to 1,000 times the luminosity of our sun. Or spectral class G, they're around the luminosity of our sun. Right? Most of the stars are there. Again, in the upper right, these are sort of the giants, really large stars that are cool, but very luminous. And there's subclasses of giants too, we'll talk a bit more about later on in the course. The bottom are the white dwarfs. Those are late stages of a star's life. At least some stars go to that stage. And they're very hot, but they're still rather dim. If you recall from earlier, when we were talking about the mass to luminosity relationship, right, that it goes as the fourth power of mass, that was good for about 90% of stars. And also, I was telling you that of the stars we see, about 90% of them lie on the main sequence. These two groupings are one and the same thing. Right? The stars that follow that mass to luminosity relationship are main sequence stars. The fundamental connection that's going on there is that all of these main sequence stars are generating their power in the same way that the sun does. That is by fusing protons together. Right? Think back to when I told you about the nuclear fusion going on in the core of the star. Most of it is this proton-proton chain, which starts out by fusing two protons together. Right? That's sort of the key first step. And if a star is doing that, then it's in a lot of ways very much like our sun, and it lies somewhere on the main sequence in that HR diagram. So if all those stars on that main sequence are doing the same sort of thing, what is making them different? It's their mass. Right? How much mass there was available when that star first collapsed. Right? So think back to what I was telling you about the formation of the solar system. There was this sort of cloud of dust, and it clumps together, or it sort of gets together enough, and it's swirling around a little bit, where it really wants to start to fall in on itself. Right? And it falls in, and a lot of it ends up going towards the very center where the sun is, where our star is, the sun. The stuff that's on the outside ends up accruing around to form the planets, but most of that material falls into the center and crushes together, so much so that it starts that proton-proton fusion. So how much stuff there was there initially that started to fall in to form that star, to form that planetary system overall, is going to differentiate these stars along the main sequence. Right? If there was a lot of mass there when the star initially started to collapse, a lot of mass ends up basically meaning that there's a lot of gravitational energy to crush down and make the interior of the stars really, really dense, really, really high pressure, and so you end up generating a lot of energy in that interior. You generate a lot of light, that star ends up being a lot more luminous. That is as opposed to if you start out with less mass, there wasn't as much dust that initially fell in to start forming that star, then it's just the opposite, right? There's less gravitational energy overall to crush down the interior, so it's cooler a little bit in the interior, it's generating less light. Overall, it's lower luminosity. It's different. I'll remind you again, and probably keep reminding you, when I say light, for the most part, I'm not just talking about visible light, right? We're talking about all parts of the electromagnetic spectrum, or the full range of electromagnetic radiation, that going from radio to infrared to visible, ultraviolet, X-ray, and gamma. So that's mostly it for this lecture. Just wanted to mention very briefly about some of this stuff that's not on the main sequence. So remember again, that's that HR diagram, temperature versus luminosity. Most stars lie along that diagonal. There's these other ones that are not. And I said a little bit about them before, but it turns out that the giants and the dwarves are basically late stage stars, right? Stars that have been around for a long time, and they've burned through or fused through pretty much all of the available protons that are there to fuse, right? So they sort of run out of their fuel. It takes a very, very long time to do that, billions and billions of years, but eventually you get there. After they burn through all that fuel, other stuff starts to happen. What is that other stuff? Well, you're just going to have to wait until we talk about the old age and death of stars to learn more. All right, yeah, this is an image that's showing you like how large Betelgeuse is if you were to stick it in our solar system. Very large. It's another star that you can see in the night sky, Sirius, and it has a companion star that's a white dwarf. In that image, the dwarf star, I think it's just down and to the left, is this little dot right there. And that's it. That's all I got for the Celestial Census. I think next time we're finally going to talk a bit about how we measure the distances to stars. I will see you then.